Hi, this is Mrs. Basin, and today we're going to talk about unit conversions. So the first thing we want to look at when we talk about unit conversions are conversion factors. So what a conversion factor is a ratio of equality between two units. So there are two values that are equal to each other. So if we look at this example, this is probably something you saw in grade school where we talked about the cups and the pints and the quarts and the gallon. So if we use our little diagram here, we could say that there are 2 cups in 1 pint. So that would be a conversion factor that would be true. So 2 cups equals 1 pint. And I'm just going to use the letters here. Then we could say there are 4 quarts. So there's 1, 2, 3, 4 in 1 big gallon. So I could say 4 Qs equals 1 gallon. I could also say there are 2 pints in 1 quart. So again, these are just things that are equal to each other. Or I could say there are 1, 2, 3, 4 cups in 1 Q or 1 quart. So conversion factor again are just 2 things that are equal to each other. Now when we use conversion factors, we will most likely be using metric conversions. So this is a table of metric conversions. We most commonly use the centimeters to meters, kilometers to meters, millimeters to meters. A couple other ones we might use, like we might use the nanometer one. So there's nanometers down here. So 1 nanometer is 1 times 10 to the negative 9th meter. We might also use 1 kilometer equals 1 times 10 to the 3rd meter, which is the same as 1,000 meters. So those are just a couple examples, and this would be a table that you would have access to if you were doing some kind of problems with those. So the reason, or the way that we use all these conversion factors is in a problem-solving method called dimensional analysis. So this is how we are converting from one unit to another using these conversion factors. So we're using this instead of moving the decimal place because, like we talked about before, eventually we're going to be converting between units that can't just move the decimal place, and we're going to do a couple examples where you can see this. So this is just a picture of the general format. You always start with the given, so this is what would be given. These 2 things would be your conversion factors. So 440 yards is 1/4 of a mile, 36 inches is equal to 1 yard, and then this is your final answer. And then this particular question would say how many inches are in 2 miles. So you convert until you get to that unit that the question is asking you about. So we're going to go through and do a couple examples here. That's the best way to learn this. So this is an easy one. How many seconds are in 1 day? So just like we said, we're going to start with what's given in the problem. So we have 1 day. Then we're going to use the conversion factors that we know to get to our final unit, which is seconds. So we know there are 24 hours in 1 day. Then we know there are 60 minutes in 1 hour. And we know that there are 60 seconds in 1 minute. Oops. Then, like we did before, you're multiplying across. 1 times 24 times 60 times 60. You're multiplying the bottom numbers across, and then you're dividing top to bottom. So if we go through and do all of that, we end up with 86,400 seconds. Okay, so now let's look at a couple that are a little more difficult than the ones that we had done before. So here's an example of one that has multiple units in it. So instead of just having 1 unit, we've got a couple units here. So it says the doctor orders 15 milligrams per kilogram of a drug for a patient who weighs 176 pounds. How many milligrams of this drug should the patient receive? So the conversion factors are given in here. Well, there's one that we would have to look up, and I'm going to give that to you as we go through. But this right here would be considered a conversion factor. There's 15 milligrams per 1 kilogram of this drug. We know this patient weighs 176 pounds. We want to solve for how many milligrams that patient should receive. So we're going to start with what we know here. We know we have a 176 pound person. Now, since this is kilograms, we have to get rid of this pounds and go to kilograms. So I would have told you in this problem that 1 kilogram is 2.2 pounds. So that gets rid of our pounds. Then this is where we can use this conversion here. We know that we need 15 milligrams per 1 kilogram of body weight. That takes care of that. That allows us to end up with milligrams so that we can go ahead and do our calculation. So we're going to multiply going across, divide top to bottom, and we end up with 1,200 milligrams. Okay, let's try one more here. So then this one says, determine the milligram per minute required to administer when the flow and solution concentrations are given. So this is for an IV, and those are given usually when someone's asked to do that, they're asked to calculate the milligram per minute required. So it says the medication is infusing at 32 milliliters per 1 hour, so that's one of your conversion factors, and the IV volume is 250 milliliters. They also tell you the amount of dissolved medication in the IV is 700 milligrams. Okay, so this one we're going to start out again with something in the top and the bottom. So we know there is 700 milligrams of medication in 250 milliliters. So that's actually what I'm going to start with here. So I have 700 milligrams per 250 milliliters. So these are a little different than what we've done before. So what do you do for this? I need to end up with milligrams per minute, and it starts out in milligrams per milliliter. So we're going to work on 1 unit at a time until we get it to where it's in milligrams per minute. So the first thing I can do here is I know that this is going at 32 milliliters per hour. So I can use that to get rid of my milliliters. So my next bracket here, I can do 32 milliliters per 1 hour. So that takes care of my milliliters. So now I'm in milligrams per hour. I need to be in milligrams per minute. So that just means I have one more calculation to do here. To change hours to minutes, I know 1 hour is 60 minutes. So that takes care of that. So then I'm going, and once I do the calculation, again, multiply and divide here, I know that I'll end up with milligrams per minute. So when I calculate this, I end up with 1.49 milligrams per minute. If I look at my sig figs here, I'm gonna round that to 2. So this gets rounded to 1.5 milligrams per minute. Okay, one more. And this deals with units that are squared or cubed. So this last one, we're looking at how many milliliters are in 3.6 times 10 to the 8th millimeters cubed. So we're going to start with the 3.6 times 10 to the 8th millimeters cubed. So this is tricky because of this cube on this millimeter here. So when we use the conversion factors, we have to take into account what that value is there. So instead of just using a millimeter here, we have to use a millimeter cubed to get that to convert. So the other piece of information I'm going to need here, and I'm going to write it up here so that we know that we can use it, is that 1 milliliter is the same as 1 centimeter cubed, or 1 cubic centimeter, 1 cc. So this would also be equal to 1 cc, like you would see on a measurement on a syringe. So 1 milliliter, you can switch from meters to liters using this milliliter to centimeter cubed conversion here. So that's how we're going to eventually get there. So the first thing I'm going to do here is I'm going to get rid of millimeters, and I can use the 1 meter is equal to 1,000 millimeters. Now if I left it this way and I didn't do anything to this unit down here, this millimeter would only cancel out one of these and I'd be left with millimeters squared. So if I want to get rid of the cubed, I have to cube this whole thing. Now the thing you have to remember though is whatever you do to the unit, you have to do to the whole thing. So when I cube this unit here, I also have to cube that 1,000 that's there. Okay, so that takes care of my millimeters cubed. But now I'm in meters cubed, I need to be in centimeters cubed so I can change it to milliliters. So my next step now is going to be to get rid of the meters. So 1 meter is 100 centimeters. But again, this is cubed, so that means this has to be cubed, which means this also has to be cubed, because anything you do to the top, you have to do to the bottom. So that takes care of that. So now I'm in centimeters cubed. Now I can use my conversion that I gave you up here. 1 centimeter cubed is equal to 1 milliliter. That takes care of that. And then I end up in milliliters. So what you have to remember, though, is when you do the calculation, when you do this one, it's 100 cubed. When you do this one down here, it's 1,000 cubed. If you don't cube those conversion factors, then you're not going to end up with the right number here. So go ahead and practice this with your calculator. Make sure you get the same thing that I have here. So if we do this correctly, we should end up with 360,000 milliliters, which we could, if we wanted to, convert that to 360 liters. Now, unless it asks you, you wouldn't have to change that, but this is a more manageable number here. So again, if it's a cube unit, you have to cube the conversion factor parts as well. All right, the last little thing we need to talk about here is density. So density is the ratio of the mass of an object to its volume. So density is calculated by taking mass divided by volume. Density is temperature dependent, so that's why density tables will have a temperature associated with them, or if you see density problems, it'll have a temperature. So the density of a substance will change depending on the temperature. Density is also an intensive property, so that means it doesn't matter how much of a substance you have, the density is always going to be the same as long as the temperature didn't change. Because of that, we can use that to figure out what a substance is. We can use it to identify a substance. So if we know the density of a substance, we can go to a table and a lot of times figure out what it is. Okay, so 2 quick problems here. The first one is density of silver as 10.5 grams per centimeter cubed. We want to know what is the volume of a 13.4 gram silver coin. So we can use our density is mass divided by volume. So all I would have to do here is my density was given. So my density is, I'm going to do this below here. My density is 10.5 grams per centimeter cubed. Okay, so my density is 10.5 grams per centimeter cubed. My mass is 13.4 grams, and I'm looking for volume. So if I go ahead and rearrange this and solve for volume, I get 1.28 centimeter cubed because my grams canceled and I'm left with centimeters cubed. Now the other thing you can do here is you could use dimensional analysis to figure this out too. So if you start with your 13.4 grams, you can actually use the density as a conversion factor. So what this is there's 10.5 grams in 1 centimeter cubed, and you will end up with the same answer here. So that's another way you could do some density problems if you wanted to. You could set them up as dimensional analysis instead of using the actual problem there. Notice I rounded to 3 sig figs on both of these because both of my numbers here had 3 sig figs. Okay, one more density problem. Okay, so here's a chart of known density. So notice it gives you the temperature. The other thing to notice here is it's given in grams per milliliter. Like we said before, this could also be grams per centimeter cubed, because like we just said, 1 milliliter is the same as 1 centimeter cubed. So it says a student finds the mass of a gold ring to be 41.7 grams and its volume is 3.29 centimeter cubed to calculate the density. Okay, so the first thing I'm going to do is mass divided by volume, so very easy calculation here. 41.7 divided by 3.29. When I do that calculation, I get 12.7 grams per centimeter cubed. Again, 3 sig figs, because I have 3 sig figs in each of the values that I'm using here. The second question is it pure gold? So that's where our table of known densities can help us. So if we look over here, gold has a density of 19.3, whereas this gold ring that the student finds is only a density of 12.7. So that means it's probably an alloy and has something else in there, and it's not pure gold because the densities don't match.